Welcome to the session, The Personalized Medicine Revolution. Personalized medicine, it has become really a buzzword, and there are so many terms used in parallel: precision medicine, stratified medicine, truly individualized medicine, ultra-personalized medicine, now preventive medicine, predictive prevention, personal health and care. And in the end, I think the interpretation matters, the innovative approach which differs. What we are discussing today in this session, I believe, is truly individualized medicine or personal health and care. And we will learn that every person is unique, that every disease is unique, that the taxonomy of diseases has changed, that we moved from studying the human genome to the personal genome, and about, for example, also epigenomics bridging the biological and social sciences. And then there had been more and more analytical and enabling tools available to support personalized medicine, to pave the way, like nanotechnology, sensors, cloud computing, 3D printing, organ on a chip, next generation sequencing, of course, CRISPR, virtual individual models, artificial intelligence, etc., etc. And now I would like to introduce you to the speakers. It's my pleasure that you're here, that I have the pleasure to moderate the session. The speakers are worldwide pioneers and innovators, and they have paved the way really for personalized medicine with a highly innovative approaches and disruptive approaches, such as, for example, the free use of personalized data and the need for intra-individual follow-up, such as deep molecular analytics and mechanistic targets for truly individualized treatments, and such as cloud-based genomic profiling services in the public sphere. So I would like to introduce to you Professor George Church. He's Winthrop Professor of Genetics at Harvard Medical School and also a professor at the MIT in Boston, US, and also founder of Nebula Genomics. So welcome, George.
Thank you.
Then Professor Hans Lehrer, he's Director Emeritus of the Max Planck Institute for Molecular Genetics in Berlin, Germany, and founder of Alagris Therapeutics. And then Dr. Philippe Menu, he's the Chief Medical Officer of Sophia Genetics in Lausanne, Switzerland, which is also a US-based company. So having said that, I would like to give now room to you, and if I may ask you the first question, George, what is the uniqueness and the beauty, I would say, of the International Personal Genome Project? You founded already 2005, so it's over 15 years ago. And nowadays, especially looking also on the Korean public health personal genome project, it seems that this is really a milestone and a longer-term perspective. Can you please tell us a little bit more about this?
Well, ever since 2005, it's intended to be a demonstration, not a scale up to 1 billion people, but a demonstration of various capabilities, including the ability to share data, the ability to return information to individuals that back in 2005 was considered radical to return to people their genomes. Still, it requires some effort to make it possible for them to share information without necessarily sharing the entire genome, without giving it away, and the ability to share cells and to test out new technologies. So some of the cell lines from these individuals are some of the best characterized genomically and in terms of stem cell differentiation, aging, and so forth. So that they're a way of testing out the personal properties of an individual with respect to various drug therapies, combinations of therapies that could interact in one person but not in others. So it's a demonstration that all of this can be personalized and shared experience.
And it's a public sphere, no? So it's open, available.
It's as far as we know, the only really open access, combining medical records, cutting edge phenotypes, and whole genome sequencing, really high quality clinical diploid genomes.
And you mentioned aging, for example, the interest in what we see. Are there also differences in populations when looking, for example, US population, where you started was a 10, I think, in the very beginning, and then the Korean. Now, is there is that very individual, or is it also that it differs between population? Is there more an intra-individual difference?
Well, I think our emphasis and certainly the expectation that has proven to be true is there's a lot more inter-individual differences, not just genomic, but age of the individual, their medical history, and so forth. There's just so much inter-individual difference. It is true that we very intentionally have started centers in London and Toronto and Vienna and Korea and so on to reflect the diversity of not just of genomes, but of culture and medical practice. And we want to reflect that in a form where people can see the full richness. If you have a fully de-identified database, you can't really practice medicine. You can't see how medicine is practiced, which is where you have a full integrated medical record, especially if you want it to be for the emerging future of personalized medicine. You want to see what that's going to look like, and that requires a really much more open strategy.
Was it very much also you experienced that a really shift in mind, of minds of also other scientists, other groups to learn from the PGP that it's always a momentum. No? It's like a photo, I think you said years ago, and we see so much in reality that it's still very much stratified and exactly not what you are, what you see and what your findings and observations are.
Yeah, I think it's important to allow many different flowers to bloom, and there is some value to the silos, but we're providing an alternative that can coexist, which is a way of sharing deep data sets that include near future technologies. So I think we can tolerate both. There has been a general tendency in our direction, which is it's hard to recruit people now without promising you're going to tell them something about their health. So that's now routine. The use of whole genome sequencing rather than SNPs, which we've advocated from the beginning, the whole genome sequencing is moving further. In fact, we now have our first actually complete full genome sequence in the world just in the last few weeks in a preprint. So I think that these are trends that you can see. It's becoming so inexpensive. You can get a nearly complete genome, clinical grade for $300 now. So it's a new world, and that's what we were trying to anticipate.
So it's no longer a matter of costs
right.
Just the willingness to do it, and
right. And communicating the advantages that even if it's only 3% of us are going to have a big advantage, you don't know whether you're in the 3% or the 97 until you until you look at the personalized medicine in your own genome.
Mm. And sometimes we, I think, looking at the epigenomics, the role I mentioned in the beginning, and sometimes, yeah, people think we are, the genomics is so deterministic, this old wording, yeah, but it comes again and again, and in some contexts with data protection or whatever. But we are understanding the social different environments, chemical, physical, biological, and that is changing the genome on a daily basis. And I think that is what for me was really 15 years, such an eye opener. So
yes, very, very important to the genome is once in a lifetime maybe, but your immunological and microbiological and transcriptional omics really should be assayed as often as possible.
Yeah, they do. Yeah, thanks, George. And I would, in the first round of questions now, ask Hans. Hans, the digital twin or the digi-twins, what was your idea behind that innovation? What's new or what is still disruptive there? What would you say?
Yes, the basic concept is, in a sense, building on what George has said. We are all different. We have different genomes, we have different environments, different disease histories, different microbiomes, different diseases which have the same names but are molecularly different. And therefore, it's not surprising that we react very differently to the therapies and preventive steps which we undergo. So this has disastrous consequences. Europe alone, we have very large numbers of people who die or get sick to adverse drug reactions. Nevertheless, the medicine comes from a model in which we assume everybody's going to react the same. First-line treatment, blockbuster drug, and this has to be replaced by a view of medicine in which everybody is assumed to be different. Every tumor is its own orphan disease and can have very different features which make it react completely differently than another tumor. But that's not the only thing which plays into the question how the patient should be treated. For example, in an oral drug, we also have to know about the microbiome, which might modify the drug in the digestive tract, about the pharmacogenomics, about the reaction of the normal tissues, about the immune system, to be able to predict correctly what the optimal therapy could be. And the digital twin is the idea to implement in medicine the same thing which we use in all other areas, an exact predictive model of individuals in which we can make our mistakes on the computer model.
What examples do you think about from other areas, Hans?
Yeah, for example, an instructive example is a jet engine, which is basically immortal. It has tens of thousands of sensors. Every jet engine, which obviously starts the same after production, is modeled individually to make sure that whenever some effect goes in the wrong direction, we correct it. This is far away from what we do in medicine. On one hand, because we know a lot more about the way a jet engine functions because we have designed it. Another aspect is probably that we are considered much more replaceable than a jet engine, and therefore there's much less effort going into how to keep people healthy than how to extend the life of a jet engine. This is a commercially important distinction, which I'm afraid we will have to live with unless we elect governments which set their priorities very differently than most governments do at the moment.
This is, and where do you see in the moment the barrier, mostly the barrier?
So I think the technology development is not the barrier. George has mentioned many of the things we can do now. And in principle, we could have disruptions in medicine just as much as in all other areas. The problem there is that medicine is highly controlled, in many cases also funded by the governments. And those controls serve not only to save, to keep us safe, they also serve importantly to keep the stakeholders' income safe. So sometimes there is I suspect there is a distinction between us surviving and the profit margins of specific groups of stakeholders dropping, and very often things go in the wrong direction. We have one particularly striking example in the COVID pandemic, in which George and I have proposed last May that we could eliminate the pandemic greatly safely and comparatively cheaply by testing everybody at regular intervals for some time till the infection was eliminated. Strangely enough, nobody was interested. We had to then develop a technology which actually was able to do it, which is now provable. We have examples of an infrastructure which would allow this to work on a population-wide basis. And we can show by computer models that, for example, Germany, I have the numbers from Germany, could have saved out of the 90 something deaths due to the pandemic, roughly 80,000 deaths, because all the deaths which happened outside of the first wave. We could have saved 6 months of lockdown by basically taking a very small number of infected and putting them for 2 weeks in quarantine, and we could have saved billions of taxpayers' money, and nobody was interested because the stakeholders probably did not see a way of making sufficient amounts of money. The paper is on a reprint server, so anybody who's interested can have a look and see if they agree with the conclusions. But I think we have a very good case in which
that's a good
the stakeholder structure has really stopped something which has would have saved many lives.
Yeah, I think it's very convincing what you are saying, and this is something really to understand why. Why is that? And now coming back to the personalized medicine specifically, and dear Philip, in I think it was 2017 that Sophia Genetics had been ranked among the 50 smartest companies by the MIT Technology Review. What do you think? What is the success story of Sophia Genetics? What is it? Is it the platform had been developed, the DDM platform, something like this? What exactly is it, or what would you say? What is the success story of Sophia Genetics?
Yeah, absolutely. So maybe just as a word of introduction, what Sophia is, we're a global healthcare technology company focused on data analytics. A large part of our focus is on oncology, but we're also active in other disease areas. We're founded about 10 years ago in Switzerland, and by now we have a global footprint. And in the core offering and asset, if you want, is this analytics platform. To understand why I think we've been successful, it's probably good to take 2 steps back and kind of look at the opportunity based on industry trends. I think over the last 10 years, we've seen a bit of a dual revolution. One, you have an explosion of the production of healthcare data at scale, usually done through high throughput modalities. NGS, next generation sequencing, is a prime example of a technology that started in the market about 10 years ago with the first Illumina sequencers, and quickly moved from research to clinical routine, right? And to this point where in oncology today, it's part of the standard of care in many cancer diagnosis steps. So you have this explosion of data on one hand, in digital format, which is very important because then that allows you the second revolution, which is AI tools and techniques and machine learning, which have really come of age over the past few years. Now anybody can build their own machine learning, deep learning models, from internet building blocks. And so the conjunction of this data, digital format production at scale, plus the analytics engines allows you to really do now, I would say, what we call data-driven medicine, which is supplementing the intuition of physicians and healthcare professionals with hard real-world data to guide a bit more the treatment decisions, right? If you think about what we call evidence-based medicine, it's not that old, right? It was somewhere in the 90s. So which suggests that, medicine has been a lot of an art so far. And I think there's a lot of room to improve and strengthen that with, I would say, more data-based decisions, if you want, in clinical decision-making. Now, the challenge to that, as always with opportunities of a challenge, we have a lot of different ecosystem-wide barriers to basically push this vision that George and Hans was also talking about making the best use of data for personalized medicine. I think the first one is lack of data standardization and harmonization. Everybody is producing their data in their own way with different technologies in their institutions, which then creates a lot of noise in data. It's hard to actually then compare and combine it. Second one, which obviously everybody is aware of, is the data silos. Everybody is producing their data locally or in centralized institutions, but they kind of get locked. And even when we talk to hospitals, they have a hard time actually reconciling the data for their own patients on their own premises because it's produced in different systems. Third one is barriers to collaboration. So even when people actually want to collaborate, we have strict rules in place for good reason, but still which hinder collaboration around data privacy, the fear of losing control of the data. What happens if, I share the data with another hospital or another investigator? And then the last two are basically, we take a very what we call a monomodal approach, which we look for, even immunotherapy today, okay, PD-L1 positive, PD-L1 negative. If you look at certain mutations, are you positive, are you negative? But it's usually like with one dimension, right? You're looking at one alteration that guides treatment selection. And the last one is a lot of the healthcare infrastructure right now is centralized, whether it's central labs, hospitals. That makes it difficult to scale up at a global level, right? So you're basically end up with more like local solutions. So from our perspective, there was an opportunity to develop and deploy a cloud-based platform, right, that has AI at the center that you can deploy at scale across the globe that can help standardize, compute, and analyze digital health data modalities. So we started with NGS because I mentioned this was the first one that came from the research in the clinical world at scale. Right now, we have about 750 different hospitals in the world working on the network in 70 countries.
Is there a specific country where you are more successfully, or where it's more easily was easier to pick up the idea?
Well, we started the hard way. We started decentralized, right? So we leave people produce their data, and we started in Europe, which, I know Hans being from Germany, data privacy, very strict with good reason, right? But not easy, which means we had to adapt to all of these local, jurisdictions and requirements and then scale up. And now we're anywhere from Europe, US, LATAM, and APAC. So I would say by now we've learned our lessons and we're good to go in every geography, right? But the point of the platform where we think there's a lot of room for a technology platform to help, standardize the data and share knowledge. We see three success factors. Number one, it has to be decentralized, right? So leave the generation of the data and the custody of the data to the users and the institutions. That's very important, and not kind of take samples and data away from people because they want to keep it and have access to it. Second is you need to be technology agnostic, which means I need to be able to process data in the same way, whether you use a specific sequencer on NGS, a scanner on radiology, because if I have to force you to use a solution, then that's not going to be scalable either. So you need to be able to standardize the data. And the third one, which is the one where we feel almost like the strongest about, is you need to be multimodal in nature, right? And we've heard about digital twin, for example, but this idea of really combining all of different data modalities together and not just looking at this one specific marker. If you look at oncology, it's very clear that at the simplest, it's a disease of the DNA, right? But if you just look at the DNA, you're just looking at something very fundamental. What you need is the phenotypic information, whether it's radiomics, radiology, pathology, clinical data. Tomorrow it's going to be proteomics, and others.
Yeah. Yeah, thank you, Philip. So I think that's really, we heard now three very different approaches, highly innovative approaches, and then observing that and knowing that, seeing that on the one hand, these ideas, these disruptive ideas, and then to have a reality check in the health systems. I would like to ask you why, and it might be a little bit bold to ask this, why is personalized medicine such a snail? Such a slow moving target? Is it because I see more and more really a difference, a discrepancy, what's doable, what's, and on the other hand, how it's implemented?
Well, I could take a crack at the beginning of that. I'm curious to hear everyone else, but in a way, it's going very quickly in the sense that the Orphan Drug Act, for example, in the United States, has made it profitable for pharmaceutical industries to aim for smaller and smaller cohorts and still be sustainable. So that's one thing. The other thing is we are getting better at databases for looking at drug interactions, drug for two drugs and drug genome. And of course, cancer is becoming incredibly personalized. So those are the successes. But you're right, there is another side, which is that the average person does not have access to their genome, even though it's dirt cheap. It's very affordable in the industrialized nations. And I think it's very similar, make the analogy to things like tobacco and seatbelts. People knew the public health advantages, but they felt like, well, I have a 97% chance of surviving. Why should I do anything about it? And I think that's something where you need very specific, either government interventions or very specific marketing on the capitalistic side to overcome it. So for example, seatbelts, it's this annoying sound that they make. It's not just installing them in the cars and having laws. So we're still at early days for getting full adoption. And it might be helpful if insurance companies or national health or employer, however the health is provided, see the return on investment, which is probably 10 times the cost of the genome on average, even for not necessarily for every individual, and they start offering it to everyone routinely, because then it becomes the norm, and it is recognized as valuable rather than something that's still off in the future. It's not off in the future. It's right here, right today.
Yeah, so many governments, businesses are looking, like you said, what are incentives, return of investment? Do we need totally different business models? Maybe that the company is following, is becoming more healthcare provider, really in a provider sense, and then following people throughout the whole life, maybe, and so thinking more per capita and things like this. But I think there's so much where also new ideas are needed, I guess.
I think to some extent it boils down to the question of stakeholders. Stakeholders are people who earn money from a specific process and not the cancer patients. If cancer patients were also considered stakeholders with a higher priority in the decisions, we would use deep molecular analysis on everybody who is treated with chemotherapy. We know perfectly well that patients get killed by chemotherapy treatment. We know perfectly well that we could find in primary tumors long before we have heavily metastasized patients in which we tend to be able to use the instrumentarium we have available. It's the same translocations, actionable variants, the same leads how to treat the people. It's just not important enough to change the system. I think we have stakeholders who slow down the adoption of new systems. Just imagine which browsers we would use if the browsers had to be approved by the FDA. So, WhatsApp is not something which is going to be easily possible in medicine, and not just because of the protection aspect. I think a big element is the protection of commercial interests, which slow down the adoption of things which probably would have an enormous positive impact on the patients.
So also lobbyism, we have another problem of lobbyism in healthcare, like we have in agriculture and other sectors as well.
Yeah, I think it's the nice thing in IT is it doesn't matter what Microsoft thinks about which browser you use. You cannot easily declare. They cannot easily declare their browser as being dangerous to the health, and therefore Netscape can take over. This is something we need more of in medicine.
Yeah. We have 3 more minutes, and I would like to give you maybe to mention also or to ask you, George, you have been a lot of times in Korea, Hans, George, in China, etc. Or Hans was, you have been to India, Manipal, School of Life Science. So for example, what can we learn also from other centuries-old knowledge experience like Ayurveda biology, the 3 body types, and then 400 characteristics explaining different microbiomes, RNA expression, etc. Why are we not looking more into these experiences, or do we?
Well, we are, in the sense that we're collaborating internationally now, and there are many things to be learned, both generically in terms of traditional medicines. They do have a multitude of compounds that have been harvested. That's on the more generic. It still can be personalized. And then I think on the personalized side, there's idiosyncratic relationships that we can learn from in terms of the cultures caring about the authority of ancestors, the experiments with 1 child per family. I think there's just many, they become more committed to the genetics of the children and in relation to their ancestors than many, say, in the far west of the United States. So I think there's definitely lessons to be learned there. They embraced non-invasive prenatal testing much more rapidly and paid for it out of pocket without requiring government or insurance help. So yes, the conversation is extremely important to be international.
One thing which will help a lot is if we include deep molecular analysis and sensors, etc., according to the jet engine model, into routine medical practice, because it's much easier to identify the values of a traditional medical compound if you follow the patient, not just by the fact if it self-describes having headaches or not, but by the effect it has on metabolite profiles, on the epigenome, on, on everything you can basically measure. And I think that's where we have to get at. We should measure everything we can on every human individual. We are as valuable as jet engines, even if governments haven't recognized that, but I think that's where we have to go to. And the technology is not the limit. We could, at very low cost, systematically analyze every cancer patient, without any problems. This is not financeable. It's just not important enough to
Final round
rescue.
Sorry, again, the final round now from everybody, please, one short last statement. Hans, would you like to one short last statement?
I think the future has begun. We have to be able to take advantage of it, and we cannot rely on many organizations and on governments to do the job for us. This is something we have to do ourselves. We are the only ones who really have our own interest in mind.
Thank you. George?
I would say, even if you're not willing to do it for yourself, you should be willing to do it for your family members. And so that's one of the key things behind precision and personalized medicine.
Wonderful. Yeah. Philippe?
I mean, from my side, I think it's clear that, AI, technology, new sources of innovation are coming of age. And I think it will have a profound impact on all of us, but also on the healthcare professionals of the future. And I start thinking about, what does medical school look like 10 years from now? Maybe you don't need to learn all of these details because, as you say, Hans, right, there will be sensors to do that for you. And maybe that gives us more room to get closer to humanity, right? Like a human interaction with the patient, which AI will never be able to do. AI will be able to help you treat the patient, probably not care for the patient, right? So I think it's maybe a way also to reimagine a bit the way we do medicine.
Many thanks to the three of you. It was really pleasure to have you here, and I got the sign we unfortunately have to now stop. So thanks a lot again, and learned so much about evolution of life today in the context of personalized medicine. Thanks a lot.
Thank you. Thank you.
Thanks.
Professor Brand.
Okay. Goodbye.
Before Professor Brand, before you go, can we thank you from Belfast?
Well, most welcome.
Well, you have a superstar for a superstar panel. Yourself from the Netherlands, Philippe Menu from Switzerland, Hans, of course, from Germany. The future is now. The future has started, Hans. We heard that, and George Church up very early in the morning, George. But we liked what you said. You said you get up at this time every morning, so you're up before 5 a.m. So it's they tell me it's the best part of the day. Can we thank you from the bottom of our hearts for taking part in this discussion around personalised and precision medicine today? Thank you from MTech Europe 2021.